Assalamualaikum warahmatullahi wabarakatuh, and very good day to all of you. So for part number 4, chapter number 4, we will discuss about the type of axial turbine design, where we will learn about the parameters that we need to consider for axial flow turbine design. Okay, for axial flow turbine design parameters, there are few parameters that we need to consider for best turbine design. So this figure shows the 3 stages of rotor in the turbine. So the first parameter that we need to consider is the outside diameter, that represented by DO. As shown in the figures, the outer diameter of the rotor of the turbine, DO. So this parameter is important because it will determine the size of the turbine, the size of the machine in terms of casing, and also the we need to determine the suitable size of the machine so that we can align with the space available that we have. Okay, so we need to align the size of the turbine and also the space available where we will put the turbine at a certain space area. And also the outer diameter also will determine the cost of the turbine in terms of the cost to design the turbine and also the cost to fabricate the turbine. If the size increase, the cost of the turbine also will increase. Okay, the second parameter is about the turbine weight, where the turbine weight is equal to mg mass multiplied by gravitational value. And in terms of weight, we can change the value of weight, the weight of the turbine, by changing by using the different type of material. Okay, so if you want to have a lighter weight of the turbine, so we need to use a very light material so that we will have a lighter total weight of the turbine. And the material cost, material price also will determine the cost of the turbine. Okay, the cost of the turbine. Okay, the third parameter is the rotor angular velocity omega, as shown in the figure, where this parameter omega has a direct relationship with the amount of work out produced by the turbine. So in terms of formula, if you look at the formula of the W out of the turbine, delta WT is equal to WT dot rate of work produced divided by mass flow rate M dot, also equal to tau moment of force multiplied by rotor angular velocity omega divided by mass flow rate. Okay. Okay, so if we look to the equation, WT represent the turbine work, tau represent moment of force, and M dot represent mass flow rate, as shown in the figure. And the last parameter, the most important parameter in axial flow turbine design, is the efficiency, where the efficiency actually is the parameter that very useful to the designer. So the parameter become a useful guide for the designer, and it will become the main focus to the designer in order to obtain the efficiency, to calculate the efficiency before obtain the final parameter for the axial flow turbine. So that's why we learn numbers of study about the factor that affect the efficiency of the turbine. So the final design in terms of parameters will lies within acceptable limit, which depend on the design requirement the minimum losses value, and also the maximum efficiency value. Selecting an axial turbine design parameter based on the efficiency. So we have two types of parameter. First, we call the selected parameter, where for this parameter we can choose the value that's suitable based on the designer requirement. So the first selected parameter is the blade profile, the shape of the blade that we will use for the rotor and also for the nozzle. And normally from the blade profile we will obtain relative velocity vector W. So the figure shows the velocity diagram at the nozzle and also at the rotor. So if you look the blade profile that you use in the schematic diagram, from the blade profile we can determine the value of W2 and also W3, especially in terms of direction of the vector, because the direction of the vector W, relative velocity, normally based on the shape of the blade profile. Okay, next parameter that can be selected is the mean blade speed U, where this mean blade speed have relation with the rotational speed of the rotor. Okay, U shown in the schematic diagram. However, the value of U is limited by the blade stress. If you look in the figures, the figure shows the cross-section drawing of the combustion chamber and also the turbine, the axial flow turbine. So we have combustion chamber and also the turbine. So the blade stress will occur due to the extremely high temperature at the inlet, where in terms of temperature at the inlet of the turbine can be higher than 1000 degrees Celsius. And the next figure shows the stress analysis in terms of heat stress analysis on the turbine blade, where we can see different colors regions on the blade, where the red color region probably due to the highest heat stress on the blade. Okay, so that we need to know the limitation of the turbine in terms of mean blade speed. So normally the maximum value of mean blade speed is around 450 meter per second. So if we use more than this value, so we will damage the blade of the turbine. Okay, the next parameter, selected parameter, is the specific work, delta W, the amount or the value of work we need to produce for the turbine, for the axial flow turbine. So we can determine at the beginning of at the initial stage of the turbine design, we can determine the value of the amount of work produced that we want for the turbine. So the specific work represented by delta W, we already learned that the formula for delta W is equal to U Cy2 plus Cy3, which is referred to the component, refer to the Y component for the absolute velocity vector. So from this parameter, we can determine Y component for the velocity diagram, such as Cy2 and also Cy3. Okay, the last parameter for selected parameter, we have axial velocity. Okay, that represented by Cx value, Cx, the x component for the velocity vector. Okay, however, the value of Cx, axial velocity, is limited by the flow area of the turbine rotor. As shown in the figure shows the turbine rotor. The flow area is referred to the what I call yellow color region as shown in the figure, that represented by flow area A1. Okay, so a mass flow rate of the fluid that enter the turbine are depend on the size of this flow area, where we have m dot mass flow rate equal to rho A1 cross section area, flow area, multiplied by Cx1, which is referred to the axial velocity. So if we increase the value of flow area, so we can increase the value of mass flow rate. Okay, m dot, and then the value of mass flow rate directly will increase the value of axial velocity, Cx. Okay, so we have Cx equal to rho A1 divided by mass flow rate, m dot. For relatively short blade, in terms of rotor blade height, we can implement the what I call two-dimensional flow condition, where we assume that the value of axial velocity throughout the process of the turbine will be constant, where we will have Cx1 equal to Cx2 equal to Cx3, and this relationship actually based on the continuity equation that we have learned before. Okay, so that's the selected parameter. The second type of parameter, we call the calculated parameter. So which means this parameter we cannot just easily select. We need to calculate by referring to the selected parameter and the others parameter. Okay, the calculated parameter is the tangential velocity, which is referred to the cy value, cy. So for different value of cy2, we will get the velocity triangle. So we will get the velocity triangle. So for different value of cy2, the velocity triangle can be constructed. So velocity triangle actually same as the velocity diagram. Okay, so from both type of selected parameters and also the calculated parameters, we can obtain or we can construct complete velocity diagram, where from the velocity diagram we can estimate from investigation data or correlation from the previous investigation in terms of loss coefficient, total to total efficiency, and also total to static efficiency. Okay, so based on this estimation, we can determine which parameter will produce the best design for the axial turbine. So in order to determine which parameter will produce best design, we need to consider the factors such as the minimum losses and also the highest efficiency. Okay, so we will select the combination of parameter if the parameter will produce minimum loss with highest efficiency. Axial flow turbine efficiency determination. So in order to select proper value of efficiency for an axial turbine design, so Shapiro 1957 already conduct an experiment or an investigation for different value of total to total efficiency and also total to static efficiency, as shown in the figures. So he obtained the variation of efficiency with cy2 divided by u for several value of stage loading factor delta w divided by u square. So Shapiro 1957 obtained the correlation in terms of efficiency versus cy2 divided by u, and the data is specific for flow condition psi equal to cx over u equal to 0.4, aspect ratio h over b equal to 3, and Reynolds number equal to 100,000. Okay, and the data or the curve that obtained by Shapiro 1957 is for stage loading factors of 1, 2, and also 3, and we need to remember that the data they obtain or the graph that plot by the Shapiro in the graph actually based on the Soderberg correlation that we have learned before. Okay, so the data for stage loading factor equal to 1 represented by blue color continuous line. Stage loading factor equal to 2 represented by red color dash line, and stage loading factor equal to 3 represented by green color dotted line. Okay, so the graph of the Shapiro 1957 will provide total to total efficiency and also total to static efficiency for various stage loading factor value. So we can see in the graph, at the upper part of the graph, we will have a different type of a curve that represent for the total to total efficiency, and also we will have 3 different lines for total to static efficiency. Okay, so if we know the value of stage loading factor and also the value for CY2 divided by U ratio, we can determine the total to total efficiency and also the total to static efficiency for the axial flow turbine. So normally all the data before we determine the efficiency, we can obtain from the velocity diagram, from the specific velocity diagram that we construct. Okay, so from velocity diagram we can determine the blade speed U, we can calculate the value of work produced delta W equal to U CY2 plus CY3. We can determine also the flow coefficient, where flow coefficient equal to Cx over U, and also the value of CY2 over U. Okay, for example, if you need to determine total efficiency and also total to static efficiency, where we assume that the data they obtained here in the example is obtained from the specific velocity diagram, where CY2 equal to 180 meter per second, CY3 equal to 100 meter per second, U equal to 95 meter per second. Okay, so from the data given, we can calculate CY2 divided by U, which is equal to 1.89, more or less equal to 1.9, and determine the stage loading factor by using this formula, where delta W equal to U square equal to U CY2 plus CY3 divided by U square, which is equal to 2.95. So due to we don't have the exact data for stage loading equal to 2.95, because in the graph we only have the data for stage loading equal to 1, 2, 3, so we just make estimation where the value is more equal to 3.0, so we can use the data for stage loading factor equal to 3, that represented by green color dotted line. Okay, in order to determine the efficiency, total to total efficiency and also total to static efficiency, just draw the vertical line for 1.9 value, for CY2 divided by U equal to 1.9. Find out the intersection point at the total to total efficiency curve, green color dotted line. So we will get the value for total to total efficiency, which is equal to 0.842. For total to static efficiency, find the intersection between 1.9 vertical line with the dotted green color line for the total to static efficiency. So we will obtain the value for total to static efficiency, which is equal to 0.680. So that's how we can use the graph that obtained by Shapiro 1957 in order to determine the efficiency for the axial flow turbine. Example 4.3, verify the peak value of the total to static efficiency mu TS shown in the figure, adapted from Shapiro 1957 for the curve marked with stage loading factor equal to 1, using Soderberg correlation and the same data used in Shapiro et al. 1957. Okay, this is the question for example 4.3. So you need to use the graph of Shapiro 1957 to answer the question. Solution for example 4.3. So in order to solve the problem, we need to draw the velocity diagram. So the figure shows the arrangement of nozzle and also rotor rows. Condition number 1, condition number 2, and also condition number 3. First, before this, we already learned that there are 3 conditions or 3 assumptions that can be made in order to simplify the analysis of velocity diagram. So first assumption, for a single stage turbine, the inlet absolute flow direction is in axial direction. So for C1 vector, we will get the axial flow. So C1 is in axial flow direction. So that the angle of flow at the inlet of the nozzle will be 0 degree. Alpha 1 equal to 0 degree. The second assumption or the second condition that we need to consider, normal stage condition, where the inlet and exit flow condition of a stage are identical. So at the inlet we have axial flow. Thus, after we consider normal state condition, so we will get that C3 also equal to C1 and the direction also in axial direction as shown in the figure. So C1 equal to C3. In terms of angle, flow angle, alpha 3 will be equal to alpha 1 equal to 0 degree. Okay, so due to C3 in axial direction, so there is no component in terms of y component for C3. So Cy3 equal to 0. Okay. The third assumption, we implement the two-dimensional flow condition where axial velocity constant throughout the stage, where we have Cx1, Cx2, Cx1 equal to Cx2 equal to Cx3 equal to C1 equal to C3 equal to Cx. So the value of axial flow is constant throughout the turbine stage. Similarly with the axial component or x component for relative velocity. So we have Cx1 equal to C1, Cx2 and Cx3 equal to C3, and the value will be the same. Based on the vector principle for velocity diagram, velocity vector of V3 can be obtained, where we know that vector W3, based on vector principle for velocity diagram, velocity vector of W3 can be obtained, where we know that by apply the principle of vector, W3 vector plus U vector equal to C3 vector. Okay, so we can draw. Okay, so from C3 and U, W3 vector can be obtained. So we can draw the velocity triangle at the outlet of the rotor, as shown in the figure. Okay, so this is the velocity triangle at the outlet of the rotor at point or at condition number 3. Okay, from stage loading factor given, where delta W divided by U square equal to 1, where the formula for delta W equal to U Cy2 plus Cy3, and due to C3 is in axial direction, thus we know that Cy3 will be equal to 0. So from such loading factor, Cy2 value can be obtained. Okay, substitute all the value into the formula of stage loading. So we can obtain that Cy2 now is equal to U. Okay, Cy2 equal to U. So based on vector principle for velocity diagram, velocity vector of C2 can be obtained, where in terms of vector Cx2 plus vector Cy2 will be equal to C2. Okay, so now because Cy2 equal to U, so vector Cx2 plus vector U equal to vector C2. So from Cy2 equal to U, and also from Cy2 equal to 2, from Cy2 equal to U, C2 can be obtained in terms of velocity diagram. Okay, look at the velocity diagram. So Cx2 plus U, so you will obtain the vector for C2. So now the velocity diagram represent the velocity diagram at the inlet of the rotor or at the outlet of the nozzle. Okay, based on vector principle for velocity diagram, velocity vector of W2 also can be obtained. So we know that a vector W2 plus vector U equal to vector C2. And we know that just now where Cx2 vector plus vector U equal to C2 vectors. Thus from these two equation of vector, we can see that W2 actually equal to Cx2 equal to the axial velocity value. Okay, so Cx2 equal to W2. Okay, from Sonderburg total to static efficiency equation, so we have mu Ts equal to the equation as shown in the slide. So where the equation will involve loss coefficient value for the rotor and also the nozzle, and also we need to determine the relative velocity value and also the absolute velocity value. And in the equation also we need to determine the static enthalpy difference H1 minus H3. So in order to determine the loss coefficient in the efficiency equation, deflection angle for the nozzle and rotor need to be determined, where the deflection angle for the nozzle is equal to alpha 1 plus alpha 2, and deflection angle for the rotor is equal to beta 2 plus beta 3. Based on the velocity diagram at the inlet of the rotor and the flow velocity value of 0.4, where the value we can obtain from the graph in the question. Absolute flow angle alpha 2 can be determined. So the figure shows the velocity diagram at the inlet of the rotor. So based on the formula of tangent formula, so tangent alpha 2 equal to U divided by Cx. Okay, substitute the equation of tangent alpha 2 into the equation of flow coefficient. So psi equal to Cx over U equal to 1 divided by tangent alpha 1 divided by tangent alpha 2 equal to 0.4. So tangent alpha 2 equal to 2.5 and alpha 2 equal to 68.2 degree. Due to the symmetrical velocity triangle or a diagram for the inlet and also outlet of the rotor as shown in the figure, so we can conclude that alpha 2 equal to beta 3, alpha 1 equal to 0 degree, alpha 3 equal to 0 degree, and also beta 2 equal to 0 degree. Thus, flow deflection angle for the nozzle and rotor are deflection angle for the nozzle equal to 68.2, deflection angle for the rotor also equal to 68.2 degree. So based on the Shapiro graph 1957, the case for Sonderburg correlation is based on case number 1 as suggested by Sonderburg, where aerodynamic load coefficient will be equal to 0.8, H over B equal to 0.3, and Reynolds number equal to 100,000. Thus, loss coefficient correlations that need to be used are zeta and star equal to 0.04 plus 0.06 deflection angle for nozzle divided by 100 power of 2 equal to 0.0679, and for zeta r star equal to 0.04 plus 0.06 multiplied by deflection angle for the rotor divided by 100 power of 2 will be equal to 0.0679. So we generalize the term for loss coefficient because the value is the same. So zeta equal to zeta n star equal to zeta r star equal to 0.0679. Based on stagnation enthalpy equation, static enthalpy difference will be H1 minus H3 equal to H01 plus half C1 square minus H03 plus half C3 square. So rearrange the equation, so we'll get the static enthalpy difference equal to stagnation enthalpy difference plus the kinetic energy difference terms. Okay, due to normal stage condition where C1 equal to C3, so we can neglect the value of kinetic energy difference in the static enthalpy difference equation. So we have, finally we will have H1 minus H3 equal to H01 minus H03, where we know that H01 minus H03 actually equal to delta W, where delta W equal to U multiplied by Cy2 plus Cy3. Okay, now rearrange the total to static efficiency equation as shown in the slide. So we have the equation for 1 over mu Ts. Refer to the symmetry velocity diagram and the calculated data, where W3 equal to C2, C1 equal to C3 equal to Cx, Cx over U equal to psi, delta W equal to U square, because the load coefficient, the delta W divided by U square equal to 1, or that given in the question. The value are already given in the question. So that's why we have delta W equal to U square. And zeta, loss coefficient equal to zeta N star equal to zeta R star. The value, because the value is the same. Substitute all information above in the total to static equation. So we'll get a new equation. So we will not have the term for zeta R and also zeta N, because we already generalized the value of zeta. Instead of we have zeta R and also zeta N, we only have zeta terms because the value is the same. Okay, and C1 equal to Cx, so that's why we have Cx term into our new equation. Okay, and no C2 terms because we already replaced C2 with W3. And again, rearrange the equation, try to simplify the equation. So we'll get the next equation based on the velocity diagram at the outlet of the rotor and also the trigonometry laws. Okay, so the figure shows the velocity diagram at the outlet of the rotor. So we can obtain that cos beta 3 equal to C3 divided by W3. So W3 equal to C3 second beta 3, which is also equal to Cx second beta 3. Substitute W3 equation into the total to static efficiency equation. So we will get this equation. So now in the equation we can see that call the term for Cx over U, where we can replace Cx over U term with psi symbol as shown in the equation. Substitute all the data obtained. Total to static efficiency can be obtained, where we will obtain that the total to static efficiency value will be equal to 0.863. Okay, this is the graph that obtained by Shapiro 1957. So now refer to the curve for stage loading factor equal to 1.0, which is represented by the blue color line in the graph. So make comparison in terms of total to static efficiency obtained by Soderberg's correlation in previous slide with the peak point value in Shapiro graph. Based on the Shapiro graph, you can see that in the graph the peak value will give the total to static efficiency, which is equal to 0.86. Now if you look at the value that we obtained in previous slide for Soderberg correlation, the value is similar to the value that obtained from Soderberg equation, which is the value that we obtained from the Soderberg correlation is mu Ts equal to 0.863. Okay, so the similarity of value obtained is because Shapiro 1957 used the same equation that suggested by Soderberg to plot the total to total efficiency and total to static efficiency graph. That's why we will get the similar value of total to static efficiency at the peak point of this Shapiro graph when the stage loading coefficient equal to 1. Okay, in order to check your understanding for part number 4, chapter number 4, please answer the question below. First question, what is the importance of rotor angular velocity in axial flow turbine design? Question number 2, what is the importance of rotor outside diameter in axial flow turbine design? Question number 3, what is the value of efficiency that obtained from Shapiro graph is similar to the value of efficiency calculated using Sonderburg correlations? So you have to answer the question by clicking the link provided in my blog. Remember that you need to know the password in order to open the link. The password was given throughout the video related to this topic. The clue is also given in the link. That's all for part number 4, chapter number 4. Assalamualaikum.